In this video, we're going to learn about the squeeze theorem and see how we can use it to solve tricky limits. Our first tricky limit is this one here. We want to evaluate the limit as x approaches 0 of x squared times cosine of 1 over x squared. So if we go ahead and try to do direct substitution, which is always our first go-to for solving a limit, if we plug in x equals 0 into the limit, we get 0 squared, which is just 0, times cosine of 1 over 0 squared, so of 1 over 0. Now, 1 over 0 here isn't defined, so this direct substitution isn't going to help us at all. Okay, so is there any way that we can simplify this limit before doing direct substitution? Anything we can cancel out? Well, that 1 over x squared is nested inside of the cosine, and we can't bring it outside the cosine, so we can't cancel it with the x squared outside the cosine. It looks like there's really nothing that we can do here. So do we just give up? Well, no, there is a way to approach this problem. The first thing to do is to notice that the function cosine is bounded between -1 and 1. Remember, cosine oscillates about the x-axis with an amplitude of 1. So the highest it reaches is +1 and the lowest it reaches is -1. Now that is regardless of the input to cosine. No matter what you input to cosine, you can't ever make it go outside of those bounds. So we have that cosine of 1 over x squared is bounded between -1 and 1 inclusive. Now we can go ahead and multiply the entire inequality by x squared. X squared is always 0 or positive, so this is a valid move with inequalities. We don't have to flip the sign at all. So of -1 times x squared, which is just negative x squared, is less than or equal to x squared times cosine of 1 over x squared, which is also less than or equal to x squared. And now let's take the limit of everything as x approaches 0. So limit as x approaches 0 of negative x squared is less than or equal to limit as x approaches 0 of x squared cosine 1 over x squared is less than or equal to limit as x approaches 0 of x squared. Now, two of these limits are easy to evaluate. Limit as x approaches 0 of negative x squared, well, we can just plug in 0 and get 0 for this limit. So 0 is less than or equal to this middle limit. This one's actually the hard one to evaluate, so we'll just write it as is. Limit as x approaches 0 of x squared cosine 1 over x squared is less than or equal to, this right one is an easy one to evaluate. The limit as x approaches 0 of x squared, just plug in 0, 0 squared is 0. So this inequality is saying that our limit is greater than or equal to 0 and less than or equal to 0. And the only number that is greater than or equal to 0 and less than or equal to 0 is the number 0. So our limit here must be 0. We must have that limit as x approaches 0 of x squared times cosine 1 over x squared equals 0. That's our big finding here. But before moving on, let's build some more intuition for what exactly we did here. Let's actually draw a graph. And in this graph, let's illustrate this inequality that x squared times cosine of 1 over x squared is bounded between negative x squared and x squared. So we'll just write that again up top here. Negative x squared is less than or equal to, why don't we color code this nice and pretty? It's less than or equal to x squared times cosine of 1 over x squared, and that is less than or equal to positive x squared. First, let's go ahead and draw x squared and negative x squared on the graph. So y equals x squared, that's just an upward facing parabola starting at the origin. So we'll draw something that looks like that. Upward parabola centered at the origin, that would be the graph of x squared. And then negative x squared, that's like the same thing but reflected over the x-axis, so it's facing downwards. Alright, so this is the graph of negative x squared. Now, the graph of x squared times cosine of 1 over x squared has to be sandwiched in between these two graphs. And because there's a cosine term, it looks like it's going to be oscillating. So it'll be going up, down, so on, up, down, all the way like this. Same thing on the other side, up, down, up, down, up, down. Yeah, this is a pretty complicated function here. So what we're really doing here is we're squeezing this function x squared cosine of 1 over x squared in between two other functions which are a lot simpler. And these two other functions start out kind of far apart, but as we approach the origin, as we approach x equals 0, the functions x squared and negative x squared squeeze together until they coincide at the origin. So initially there's a lot of wiggle room for our function x squared times cosine of 1 over x squared. It's oscillating up and down, up and down, up and down, but as it approaches x equals 0, the oscillations get smaller and smaller. There's less and less wiggle room because its upper and lower bounds are converging at the origin. So that tells us that the function has to pass exactly through the origin because it's not allowed to wiggle up or down at that point. The upper and lower bounds are both 0. So we are squeezing the limit of x squared times cosine of 1 over x squared, as x approaches 0, between the two limits of negative x squared and x squared as x approaches 0. And the squeeze theorem here just states that this is a valid thing to do. Our next problem is to evaluate the limit as x approaches pi of f of x if it is known that f of x is between cosine of x minus pi and sine of x minus pi plus 1 inclusive. Now, just to get an intuitive feel of the problem, it might be a good idea to sketch these graphs of cosine of x minus pi and sine of x minus pi plus 1 before actually applying the squeeze theorem. If you do that, you'll really see the squeezing take place visually. But for the sake of time, we won't actually do that here. To apply the squeeze theorem, all we really need is this inequality. So let's go ahead and apply the limit as x approaches pi to every expression within the inequality. So we've got the limit as x approaches pi of cosine of x minus pi is less than or equal to the limit as x approaches pi of f of x, which is less than or equal to the limit as x approaches pi of the whole expression sine of x minus pi plus 1. Now we can go ahead and compute these limits just by direct substitution. Just substitute in that pi for the x here. We get cosine of pi minus pi, which is just cosine of 0, is less than or equal to limit as x approaches pi of f of x less than or equal to, again, go ahead and substitute in that pi for x here. So sine of pi minus pi, and pi minus pi is just 0, so sine of 0, then plus 1. Now, cosine of 0, we know that's just 1. So 1 is less than or equal to limit as x approaches pi of f of x is less than or equal to, well, sine of 0, that's just 0. And 0 plus 1 is just 1. Now, according to the squeeze theorem, we know that our limit is between 1 and 1, and the only number between 1 and 1 is 1. So that's the value of our limit. Our limit, as x approaches pi of f of x, is just equal to 1. Now we want to evaluate the limit as x approaches 0 of x cubed times sine of 1 over x to the 4th. So our first goal is to bound this function somehow, x cubed times sine of 1 over x to the 4th. And when we think of bounds, the sine part jumps out to us because we know that sine of any number, including 1 over x to the 4th, whatever number that may be, has to be between -1 and 1 inclusive. So now what we'd like to do is just multiply everything in this inequality by x cubed, and that would be grand, because we could just take the limit and be done. But there's a little issue. Depending on whether we approach 0 from the right or the left, x could be positive or negative, meaning that x cubed could also be positive or negative. And if it's negative, then we'd have to flip the signs of the inequality. So it looks like one option would be to split this limit up into its left and right limits, and apply the squeeze theorem on both of those individually. But that'd take a lot of work, and really there's a much easier way to go about this problem. Instead of writing the inequality like this as a double inequality, let's just write this as a single inequality using absolute value. So we'll say that the absolute value of sine of 1 over x to the 4th is less than or equal to 1. So this is the same exact inequality as the one above, but it's just written a little bit differently, a little bit more concisely. Alright, so now let's think again about trying to get this x cubed into that inequality. Now you might say, well, the problem's still not solved, because x cubed could still be positive or negative, and if it's negative, then we'd have to reverse the sign of this inequality. And you'd be right, but there is a way around this with absolute value. We can multiply both sides by the absolute value of x cubed, because the absolute value is always guaranteed to be non-negative. For clarity, let's write this 1 more like a 1, so that we don't confuse it with absolute value. Now we can go ahead and simplify this inequality. On the left-hand side, we can just combine both of these into a single absolute value of x cubed sine of 1 over x to the fourth is less than or equal to 1 times absolute value of x cubed, which is just absolute value of x cubed. And now we can go ahead and apply our limit. Limit as x approaches 0 of the absolute value of x cubed times sine of 1 over x to the fourth is less than or equal to the limit as x approaches 0 of absolute value of x cubed. The right-hand side limit is easy to evaluate. Let's go ahead and write this again and evaluate that right-hand side limit. So limit of our function x cubed times sine of 1 over x to the fourth is less than or equal to, just sub in 0 here, 0 cubed is 0, absolute value of 0 is 0, so 0. Now, since the limit of an absolute value is the same as the absolute value of a limit, we can go ahead and put that limit symbol into the absolute value. Limit as x approaches 0 of x cubed sine 1 over x to the fourth, the absolute value of that is less than or equal to 0. And hey, absolute value is always either 0 or positive. So if the absolute value of something is less than or equal to 0, well, it has to be equal to 0. And that means that the inside expression inside the absolute value must be 0 itself. So there we have the final conclusion. Limit as x approaches 0 of x cubed times sine of 1 over x to the fourth must be equal to 0. So the takeaway from this problem is, if you're ever in a tricky situation where you think one of the terms, like the x cubed here, could be positive or negative depending on which side you approach the limit from, just turn your initial inequality into an absolute value inequality and then work with the absolute value of that term, which is always guaranteed to be non-negative. So now we know how to use the squeeze theorem to solve some tricky limits. And in the future, we'll begin learning more about the uses of limits in the context of continuity and differentiation.